Okay, can people see my shared screen? Good, okay.
Yes.
All right, so a few announcements first. There's a few things due this week. Well, homework 1 is due on Friday at midnight. So make sure that is on your calendar. Quiz number 1 is going to be next Tuesday. So next Tuesday, we will not have recitation, but instead we'll have the quiz. Okay, so online we provide a lot more detail, but essentially quiz number 1 is going to be available starting at 7:30 in the morning, and it's going to close at 4 p.m. When you log into Gradescope, the moment you open the quiz, you have 1 hour to finish the quiz. So you need to set aside 1 hour time on the day of your quiz to try to solve all the problems. For quiz 1 review, we have set aside the following hours. So Monday actually is a holiday, but thanks to our TA, next Monday, right before the quiz, we have 2 hours of office hour for quiz 1 review in case you have last minute question when you're preparing for the first quiz. And quiz 1 is going to be on chapter 1 of the textbook. And in terms of lectures, it's lectures 1, 2, 3. That's what's going to be covered. Essentially, it's going to cover number sequence as well as propositional logic. Okay, on Friday, we're also going to have review hours, and it's going to be from 1 to 3 and then 3 to 5. 3 to 5 is actually with our newest TA, Yoking. And additionally, is actually just decided yesterday between 12 a.m. to 12 noon. Also on Friday, you are going to have additional office hour with Zoe. So Zoe is supposed to have office hour on Monday, but Monday is a holiday, so she's moving her office hour to Friday to help you again prepare for quiz number 1. But James has agreed to give additional office hour on Monday between 3 and 5, even it's a holiday. Very important announcement for quiz 0. So we call it quiz 0 because this is for you to test whether you know how to inner working of Gradescope to simulate the scenario involved in a quiz. So quiz number 0 is going to be released tomorrow, again from 7:30 until 4 p.m. on Gradescope. So once you log into Gradescope, you click on quiz 0, the clock will start ticking, and you have 1 hour to answer the question from quiz 0. In this case, there's only one single problem and it's not graded. But what you need to do is try to say, I'm going to solve this question and I'm going to scan my solution as a PDF and upload it through Gradescope within the time I was given. We built in 15 minutes of grace period. So you have 1 hour to solve your quiz and you have additional 15 minutes to submit it through Gradescope. Make sure that you're not budgeting those 15 minutes to solve your actual quiz problem, but those 15 minutes is really just for the time set aside to submit. When you submit, there under the Canvas, there's a specific section talking about exams under modules. So make sure you read that carefully of how you actually submit your solutions. But specifically, the most important part for a quiz is to try to match your problem against your outline. And another thing that's important is that you have a pledge and then you have the rule page. So the rule changes occasionally from quiz to quiz, but it's still fairly generic. It talks about how you submit your solution either in a pen and pen. If you write it down under a pen, then you scan it as a PDF. If you're using a Word, we have a Word template. If you're using LaTeX, we also have a LaTeX template. The pledge page is very important because this is sort of a take-home online exam. So the only thing you're allowed to use is your index card, which is a 2-page index card. And then for quiz 0, please try to set aside time tomorrow to try to go through that submission process itself so that you know how the inner working of Gradescope works, and then you know that how a typical quiz is set up throughout the semester. And also for the future quiz, because there's going to be 5 quiz plus 1 final exam, on the day of those quiz and exam, of course, we will not have recitation. And again, I want to emphasize that you're allowed having an index card, and when you submit, you need to submit your signed pledge, your solution, as well as your index card. So that's another thing to to pay attention to. An index card is a typical size of this size, and you can have double-sided as well. Okay. And then,
there's a question in the chat that asks if they will be penalized if they didn't submit an index card if they didn't make one at all.
If you don't have one, well, actually, I have not thought about this. If you don't have one, then you would match your submission with an empty page. So their outline is going to have outline to say where's your index card. If you submit empty, like an empty page, then we can just say, okay, you did not use any index card. But it's very important to emphasize that our quiz is actually closed book, closed internet. You should not talk to your classmates during your exam. You should not be copying other people's solution, either it's from online or elsewhere, and so on and so forth. And any of those things are considered academic misconduct, and then the policy for this class for academic misconduct is a failure for the class. So yeah, so the only thing you are allowed is an index card, and it can be double-sided, and so on. Okay, so there's another question regarding regrading that came up. So we kind of clarify that further in the syllabus. If you want to have a regrading for homework and quiz, it's basically you can request regrading through Gradescope. And you have to make a regrading request through Gradescope within 1 week of receiving the grade. The only thing that is an exception is a problem set. Okay, so some students were asking question, how do I request for regrading for problem set? So first of all, it happened fairly rarely that the problem set needs a regrade. So the procedure is as follows. When you think that you have a particular solution correct in the problem set, and somehow the automatically graded Canvas tells you that it's wrong, and then you wasn't sure, then you should post a question under Piazza under the lecture number. For example, if you just did lecture 4 problem set, then you just post a question into a private message to the teaching staff to say, hey, this is for lecture 4 problem set. I provided this solution, but it was graded wrong by the Canvas. Would you please explain to me, is my solution still correct? I believe my solution is still correct. Here's the reason why. And in a majority of the cases, it's actually a mistake made by the student, which does not require a regrading. But if the teaching staff, which including instructor and TA, in that thread decided that, okay, indeed, your solution is correct, but Canvas did not cover that particular case, then what we ask you to do is to submit a formal regrading request. So you need to submit in the same folder. You are going to put a separate message to say regrading request. And then the TA who in charge of regrading will take that request and adjust your grade on Canvas directly. So the regrading for problem set is actually quite involved because it's automatically graded quiz by Canvas. It's graded by the computer. So for example, there's a few small minor cases that might require regrading. For example, if you put an extra parenthesis inside a logic expression, we may or may not have that particular solution encoded in the solution sets. So those are a few rare cases that require regrading. But once you have submitted formally the regrading request after the teaching staff have decided, yes, this indeed, need a regrading, then you need to submit this request because we have a specific TA who's dedicated in keep track of actual regrading request. So once you submit it, the TA will be in touch with you to say, hey, I have updated your grade. But we need to see that request because majority of those discussions surrounding problem set does not require regrading. Does that make sense? Okay, so as I want to point it out that the material is going to get harder and harder as we go along. Quiz number 1 typically is fairly easy. Quiz number 2, which is on proofs, is going to be quite challenging for some of the students. So I would encourage you to utilize the office hours and Piazza to ask questions when you are preparing for the exam. Again, I want to emphasize for the exam, you want to match your question to the pages under your Gradescope. And another important part, which is written here, if you want to get full credit for some problems, you should show your work. Okay, sometimes you can get partial credit for exam questions. Again, the last bit is, only thing allowed for the exam is 8.5 by 11 index card. Okay. All right. Any questions before I move to the practice question for today? Okay. So now I'm going to give you 1 minute. those are some of the practice problems surrounding chapter 1 over logic expressions, number sequence, and so on and so forth. That's what's going to be on in the first quiz. So this should be a fairly simple thing. I'm going to give you 1 minute. So the idea is you try to solve it on your piece of paper there, and we're going to go through this together. Okay, do I have a volunteer for the first question? What would be the quantifiable thing? Someone was raising hand. Cameron, yes. Do you want to unmute yourself?
Yeah. So I'm not sure how to say like
for or whichever symbol you use, right? For all exist symbols.
Yeah, so I use the for all and then X within the Z.
Yep.
And then comma X squared plus 1 is greater than 0.
Okay, perfect. Thank you. Yeah, so this is just, a typical question over, for study propositional logic is taking an English statement and translate it into, mathematical notations with quantifiers. And this exactly, so one additional question, is this statement true or false? For any integer, right? For every integer, the square plus 1 is bigger than 0. Is this true or false?
There's answers in the chat that says true, and there's one that says false.
Okay, so if you want to prove this is false, you need to find one counterexample, meaning that you need to find one integer whose square plus 1 is not positive. It's either 0 or smaller than 0. Okay, this statement is actually true because if you think about integers, integer can be negative, 0, or positive. If it's 0, then 0 squared plus 1 equal to 1 is bigger than 0, so that's great. If it's either minus 1 or 1, for example, if it's 1 squared, if it's non-zero, the integer square is bigger or equal to 1. And then that plus 1 is bigger or equal to 2, so it's bigger than 0. So you actually kind of go through a proof process in your mind to prove this is indeed true for all integers. Later on, we'll go through a few examples of proofs, and you can actually go through the same process to prove that this statement is true. Now, do I have a volunteer for the second one? You can raise your hand. We have Peter raise a hand. Go ahead.
Yeah, so for every n element z to the
for every
comma, well, no, exists, sorry.
Okay.
The e, the backwards e, and element z,
yep,
comma 2 to the n equals 32.
Okay, while you're here, is this statement true or false?
False.
Why?
Oh wait, true. Wait.
Okay, why is it true?
Because 32 is a power of 2.
Power 5.
Power 5.
Yeah. So again, when you want to prove it, right, there exists integer who's 2 to the n to the 32. If I find this integer that satisfies this condition, then this statement is true, right? Because it said there exists one. And now you find it. Okay, so this statement is true. Okay? But thank you. I think your statement is correct. Okay, So if there's no question, let's move on to the next one. So now we have a slightly more complicated thing. First, you translate the English statement into a proposition, and then you negate the proposition, okay? So again, you have roughly 1 minute. Okay, do I have a volunteer for the first question? First of all, we're going to translate English to a proposition, and then we're going to negate it. I have Andrew. Go ahead, Andrew. You can unmute yourself.
So for all x elements rational R, where x is this exclusive or inclusive?
Let's say inclusive.
Okay, the -2, yeah, inside that range, such that comma x squared is less than or equal to 8 and greater than or equal to 0.
Yep. Okay, so this problem, I didn't specify it's R, but that's okay. We can assume it's R for the time being. You can also just write it to say like this, right? If I didn't say it's R, but if you just assume it's R, that's fine. It's a real number, but that's okay. So let's say now I want to negate it. So what would be the negation? What is the negation equal to?
It's equal to there exists an x less than -2 and greater than 2.
Yeah, so it's still in this range, right?
Okay.
And then?
Or with the, yeah, okay. Such that 0, right, the x squared is less than 0 and greater than 8.
What is it and or is or?
Just or is just greater. It's or, yeah.
Yeah, so actually this is an important part of this problem. For example, if this thing here is x squared or bigger or equal to 0 and x squared smaller or equal to 8. When you take negation of 2 and, we negate it. It's De Morgan's law, right? So you actually have or instead. So now it's x squared smaller than 0 or x squared bigger than 8. Cool. Since you are here, I'm going to ask you one question. Is the original statement true or the negation is true?
It's the original statement is true.
Yeah. So that means for or integers that are between -2 and 2, its square is between 0 and 8. I mean, when you're thinking about this one, the process is to say, okay, the maximum integer in here is either -2 or 2, where the square is at most 4. And of course, it's within this range. And the smallest square in here is when x is equal to 0, then the square is 0, which is bigger or equal to 0, right? So this is true. Okay, all right, thank you. So do I have volunteer for the second question?
Again, there's a question in the chat that asks, x being between -2 and 2 does not change when we negate the statement.
Sorry, can you say that again?
So the x being between -2 and 2 did not get negated. Like, why is that?
Oh, yeah. So if you think about logically, right, the original statement is for all number that is between minus 2 and 2, some condition satisfied. The negation of that means there exists at least one exception that is in that range where the statement is not true. That's why the negation, if you look at the negation that is described in the textbook, when you negate for or, right, the or symbol became exist symbol, but it does not change the range of my proposition condition. Okay, so that is a rule you use to negate a predicate. Okay, so another thing to think about, what is the opposite condition of what I highlighted in yellow? What I highlighted in yellow is a condition to say every single number in this range satisfies certain condition, which is what I have in pink, okay? If I think about logically, what is the opposite opposite thing of this statement is to say there exists some number in this range where my condition no longer hold. That is opposite. So that's why when I take the negation, I actually don't change the range at all. It's just to say, there exists one number that is in this range where the condition no longer hold. That's what this negation means. Okay. Do I have another volunteer for question number 2?
I can try giving a shot.
Yeah, go ahead.
So for this one, we can do the backwards E,
Okay.
N, the exists, Z sign integer, the negative, and then
like this?
yeah, and then the arrow sign for n plus 2 greater than 1.
Yeah, cool. What is the negation?
So the negation of this is going to be every n inside of, would that still be the Z integer minus, or would that change to a positive in this case?
No, you don't change
negation?
the domain. You don't flip the domain, remember? This was the
okay.
previous question, right? So because the original statement is like every number in this range satisfy a condition, the negation of it is there exists a number in the same range that doesn't satisfy the condition. Okay.
Gotcha. Okay, so yeah, that, and then for n plus 2 less than 1?
Less equal to 1, okay? The important part, when you have bigger, then the negation have to include equality here. Okay, so the original statement is true or the negation is true?
Let's see. I think it's the original statement.
Yes. Well, okay, let me think. Original statement, I'm not sure. So the original statement, there exists a negative integer, so that 4n plus 2. If you think it's true, what is your example?
Never mind. That's right.
Okay, so if the original statement is not true, then the negation is true. Okay, right. So in this case, the negation is true is because for or integer that's negative, 4n plus 2 small or equal to 1. The way to check it is to figure out what is the smallest negative integer that is, or what is largest negative integer that is minus 1. Minus 1 times 4 is minus 4, and plus 2 is minus 2. And it's definitely smaller or equal to 1. Okay, so you can check essentially for this. So the negation is true in this case. Okay, all right, thank you. So the next one is going to take a little bit of time. So here, let me explain it why you do, and I'm going to again put 1 minute to it. So there's a few things. One is theorem 2, which is on theorem 2 of the textbook. This is a bunch of logic equivalences you're going to use. And then this is a likely question you're going to see in exams, by the way. And then the other thing I want you to use is using substitution and also property of implication. What I mean by property of implication in here, I mean P implies Q is logically equivalent to not Q implies not P. That is what I mean logically, the properties of implication. So to prove this, I specify you need to use this rule, and also specify you can use some of the rule from theorem 2. And then what I mean by precedence is basically there is some ordering of a priority of operations. For example, if I have P and Q implies R. I kind of already showed you. The precedence is saying that I need to evaluate P and Q first before I evaluate the implication. Okay, so precedence is really just order of how you evaluate a logic expression. Okay, so you have 1 minute to think on the high level how you prove this. And then I will give you a hint for this particular problem is that you are going to use a few rules on the theorem too. And it's very important when you actually try to prove logic equivalences to not skip steps, right? So when we ask for the proof, you want to use to say, oh, what did I do in this step? And do not jump steps either. So you want to provide as much detail as possible when you go through this proof. I think someone is raising hand. Did you? I only see Faye. I think I see Cameron. Cameron, go ahead and unmute yourself.
I just had a question. So for the quiz, are we gonna have to do commutative property?
Yes, as much as you can.
Okay.
Yeah.
Thank you.
I know sometimes we do use commutative property without even consciously realizing it, but I think it's important to try not to miss it. Okay. And also I mentioned that if we ask this type of question in quiz, we will provide theorem too at the bottom, so you can refer to it. But it's a good practice for you to put it in your index card because it's a good review process for you to get familiar with all the rules. All right, so do I have a volunteer? What is a large picture for getting this proof? I have Peter raising hand. Go ahead.
Okay. So first off, I did the contrapositive, switched the sides and negated both sides.
Okay.
And then I used De Morgan's in reverse on the left side, and that left me with a double negative on the left side that I could cancel out, leaving R and S.
Yep.
And then on the right side, then De Morgan's forward, and that left with the final result.
I think what you express is exactly the good solution, but I'm going to do it slower. I'm going to repeat what you just said, but it's slightly slower. The first thing, which is a step where you may or may not need to specify, but I'm going to specify it just to give you a sense of where I'm what I'm doing. So first of all, I'm using the rule of precedence, but this is just putting parentheses into places where I think the evaluation happens first. Okay, and of course, in most exams, you don't have to do this step, but I'm just be careful. And then the next step is exactly what you said, is I'm going to apply the rule where P implies Q is equivalent to not Q implies not P, right? Which is contrapositive, has logical equivalences to the original statement. So in this case, the P part is this part, the Q part is this part. So P implies Q is equal to not Q implies not P. So this is what you're saying, you're applying this rule. Is that correct?
Mm-hmm.
So I'm going to specify step by step. So this is now me bringing negation to Q implies negation of P. And then you said the next step is what? De Morgan, right?
Yeah.
So De Morgan's law here is, because if you look at De Morgan, is bringing negation inside, oh, sorry, that's double negation here. If you bring negation inside an AND operation, it became an OR operation. If you bring negation to an OR operation, it becomes AND operation. So one way to remember negation, De Morgan, is that you flip the arrow direction, okay? So the first term, where when I do the negation, then I'm going to do negation of R and become AND, right? Flip the arrow, negation of S. And then now the second term, I need to bring the negation inside, which is negation P or negation Q. Perfect. And then you said the next one is double negation, correct? So double negation is to say that when you have double negation, it's the original variable itself. So you have double negation for the first term, which is double negation R, which is R, double negation of S, which is S. And pretty much here you are done, but I just want to run one more step just to get rid of parentheses. And then this is again based on precedence. Okay. Any questions so far? Okay. All right. So that's a practice problem surrounding propositional logic. In discussion sessions on Thursday, you're going to see more of those practice problems. And one important thing I want to emphasize is that you should definitely do practice quiz number 1, which is available over Canvas. And try to see if you can solve all the problems and match your solution against the provided solution. And if you have any questions, again, ask those questions during discussion sessions or come to the office hour. Okay. So now let's take a quick review of proofs, simple proofs step by step. There is a 5-step process for proving the following proposition. For any rational number R, the number R plus 1 is rational. So what we do is the big capital letter Q represent rational number. So the first step we do is to translate, if the proposition is an English statement, we translate it to some mathematical proposition. In this case, it says, my statement is if R is irrational, then R plus 1 is rational. So it belongs to the set of rational numbers. So the most important part of this question, right, is that, this is a quick review, so I'm just going to go through this step by step. The most important part of this question is what is a definition or what is a property associated with something being rational? So this is step number 2, is if R is a rational number, which is part of the hypothesis, what is a property? If something is a rational number, by definition, it can be expressed as the division between 2 integers. So there exists integer a and b, where R is a divided by b. That's a definition of something being rational. Sorry. Okay. And now the next thing we're going to see is that the most important step is step number 3. Is now we have the hypothesis, we want to express the conclusion in the form of hypothesis. The conclusion is, I want to prove R plus 1 is rational, right? So this first part is hypothesis. This part is conclusion. So the conclusion is I want to show R plus 1 is also a rational number. And what I do is I'm going to use my hypothesis. So in here, I'm going to express R plus 1 by substitute R by a divided by b. And then I'm going to do a bunch of algebra, right? So it's a over b plus 1 is equal to a plus b over b, because b over b is equal to 1. This becomes a plus b over b. And then I'm going to define c is equal to a plus b. So now R plus 1 is equal to c plus b. So the 4th step is I need to take care of some, I'm not 100% done yet. In fact, this is another important step in the proof. I have expressed R plus 1 as a division of 2 things, C and B. B is already integer by original hypothesis. Now I need to show C is indeed integer. Okay, so this step is to show C is an integer. And here, this is a lot of rules you're going to use a lot is by closure property of integer. So integer is closed. So integer is closed under, there's a few operations, addition, subtraction, and multiplication. But integer is not closed under division, right? If I take 5 divided by 3, you don't get integer, but 5 times 3 is integer. So in this case, because C is equal to a plus b, both a and b are integer, and it's closed under addition, so C is integer. So now R plus 1 is expressed as a division between 2 integers. Therefore, R plus 1 is rational. Again, I'm using the definition of something being rational. Okay. All right, so that's a 5-step we need to go through. So now I want you to apply these 5 steps to this following thing. And I'm going to give you actually 1 minute to think. I said 5 minutes because it's a very generous estimation if you're doing this all by yourself. But I want you to think on the high level how you would want to write a direct proof for this. Again, the important part for this whole proof is rely on what it means for an integer to be even. What is the definition of it? Okay, so do I have a volunteer on how you would approach this problem? And I kind of sketch out the steps I would take to solve this problem. Anyone? So the first thing you want to think about is when I say something is even, right? What is the property associated with something being even? Or what's the definition of something being even? Okay, I have Dane. Go ahead.
So could we say a definition of even, for a number n to be even, there must exist some integer m such that 2m equals n?
Yep. Perfect, right? That's really at the key point of this is that when I see something is even, that m, n is equal to 2 times m for some other integer. So you can, another way to say it, if you translate it, another way to say is n mod 2 is equal to 0. That means if I divide by 2, there's a 0 remainder, or 2 divide n. This is not a notation when it says division, but in this particular proof, we really need the property that if something is even, then it can be expressed by 2 times some other integer. Perfect. Okay. So do you want to finish the proof since you go over the first hurdle? Do you want to finish the proof?
I'll give it a shot.
Okay.
So we can substitute, therefore, 2m for n and say that 2m plus 8 is even.
Okay, so because I need to now work, so this is step number, so actually this is really the step number 2 or 3 now, is that by substitution, right, n plus 8 is equal to 2m plus 8, right? Okay, and then what's the next step?
You factor out a 2 to get 2 times m plus 4.
Yep. Okay.
And because m and 4 are both integers, m plus 4 will still be an integer, and 2 times any integer must be even.
Okay, so by closure under addition, let me say, maybe I will say k is equal to m plus 4, and k is an integer, right? Because m is integer, 4 is integer, m plus 4 is integer, k is integer. So now n plus 8 is 2 times k for some k that is integer. And then you say by definition of even, because now n plus 8 is 2 times some integer. So by definition of being even, n plus 8 is even. Okay. If I go back to, the steps that is going through here, let me use in this here, let me use A, B, C, D, E step. The step number A, which we kind of skipped quickly, is basically when n is even, implies n plus 8 is even. The step B is basically this property here. Let me use actually green. Is to say what is the property of a hypothesis. The property of a hypothesis is that if it's even, then it can be expressed as 2 times some integer. And then step number 2 and 3 here is C here, which is algebra, right? We are using substitution. We are going to express the conclusion in the form of hypothesis. And then this is D, step 4 is D, which is study some detail. One of the most important parts of the detail is to show m plus 4 is indeed also integer. And then you go into step E, which is prove that by definition of even, it satisfies the definition and the proof. Okay. So now we have warmed up. Let's go over the next one. Okay. So next proof, we want to say for all integers, if n squared is even, then n is even. So for this lecture, I'm going to give you a hint, right? Is that actually proving this directly, this implication directly is harder than if you were proving the contrapositive statement. Okay, so now first of all, can someone tell me what is a contrapositive statement of this? P implies Q, where P means n squared is even and Q is n is even, right? So the original statement is P implies Q. What is a contrapositive?
That would be n is odd, then n squared is odd.
Yes, exactly. So P implies Q is not Q implies not P. So contrapositive statement is if N is odd, then N square is odd. So now you have 1 minute to think about what is your proof for this one. Okay, so again, similar to the previous problem, now I need to rely on the property of something being odd. So, what is the property of something being odd? Previously, when I say something is even, then it can be expressed as 2 times m for some integer m. When something is odd, you need to think about the same direction, right? You need to express algebraically what is an odd number looks like, and then using some algebra to show what does n squared looks like. So let me give you a further hint as you think about this, is you're going to use this following rule. A plus b squared is equal to a squared plus 2ab plus b squared. This is a basic algebra rule you are going to use in the middle of this proof. Okay, do I have a volunteer? So I kind of list the outline of this proof, what it's roughly going to look like. What is the definition of something being an odd number? What can it be expressed by? Okay, I have Peter.
There are answers in the chat.
Oh, sorry. Who said first?
There are answers in the chat that says 2m plus 1. There are 3 answers in the chat. Yeah.
Cool. All right. So since somebody already put it in the chat, let's do it together. So in this case, I have, by definition of odd, if a number is odd, this is equal to 2m plus 1 for some m that is integer, right? So there exists some integer where n can be expressed by 2 times that integer plus 1. Another way, if people thinking about, odd number is if it's, take a quotient of 2, it has a 1 remainder. That's another way to think about it. But for this proof, I need this property. So the next step, so I guess Peter was the one who volunteered. Do you want to do the next step by substitution?
Sure.
Okay.
So then you substitute this definition for n into n squared. So that's 4m squared. Oh, well,
Yep.
Yeah.
Keep going.
4m squared plus 4m plus 1.
Yes, this is precisely the step of using this particular rule, algebra rule right there. Okay. And then what's the next step?
Then we factor out 2.
Factor out 2. So n squared is equal to 2 times 2m squared plus 2m plus 1. Okay. And then
we substitute a new integer that's equal to 2m squared plus 2m.
Yep. And here, the important part is closure of integer under addition and multiplication. What is the variable you use?
C
Yeah.
equals 2m squared plus 2m. It's an integer.
This is because it's a multiplication of integers m and addition of integers, right? So by closure property, integer is closed under addition and multiplication. So c is integer. So now n squared is equal to 2c plus 1 for some integer c. Okay. Then by definition of odd, n squared is odd. That's the end of the proof. Okay.
There's a question asking, can we not factor out the 4 instead?
If you factor out 4, okay, I'm going to use a different color so we don't confuse people. If I factor out 4, you will eventually still get back to 2. Because if I do 4, this is to say that, you need to prove that an odd number can be also be expressed by 4 times some integer plus 1. Okay, because the known property is if something is odd, it can be represented as 2 some integer plus 1. But now if you use this, you need to prove that this is also indeed an odd number, because you have not proved that 4 times integer plus 1 is always odd. Okay, so ultimately you will have to prove this is odd, you need to still go back to this. Right? Because this can be expressed as 2 times this plus 1. Because odd number quotient 2, take a quotient, has remainder of 1. But the quotient operation is quotient with respect to 2, not 4. Okay? Okay. All right. So we have a time. This one is actually really hard. I put it 10 minutes, but obviously we don't have 10 minutes for it. What I want you to do is to spend the next 1 minute to think about this. Okay, this is an example of proving by case. What we can do is talk about what other cases are there. And again, a lot of those proofs are relying on the idea of whether something is divisible by 3. So when you think about it, when something is divisible by 3, what is the property? Is that it has a 0 remainder. But if it's not divisible by 3, what does that mean? For example, here, if it's not divisible by 3, that means if I take quotient 3 or mod 3, I have what type of remainder do I have? Okay, so that is what you want to think about for this question. And when I say proof by case, the idea is you divide the condition, the hypothesis, into multiple cases, and for each of the case, you want to prove the conclusion, right? So this is another proof techniques you're going to see is proof by cases. So we're going to talk about essentially, there is a few cases, and we are going to go through one of those cases, and then you can prove the second case on your own. And again, I have more problem in the end of this for this slide deck. So it's useful for you to go over some of those problems on your own, and then come to discussion and office hours if you couldn't figure out how to solve those problems. But I want you to try them first. Okay, so do I have a volunteer who tell me what other cases are? Do I have a volunteer?
There are a few answers in the chat. Someone says not divisible and divisible by 3. And there's another one says n is even or odd. There's one that says remainder 1 and remainder 2.
Okay, so let me address those 3 possible solutions. The first one isn't completely correct, because when I say resolve by case, the case has to be part of the hypothesis. The hypothesis is already assumed n is not divisible by 3. So my cases has to be fall under that general umbrella. So the second thing is that whether something is even or odd is actually quite interesting, is that you can try with that assumption, but I'm saying that that assumption, those cases, it's not directly related, again, with the hypothesis. The hypothesis is really factored into the condition whether it's divisible by 3. Therefore, the third answer is actually correct, is if it's not divisible by 3, what is the condition, right? So if I take any integer, if I take mod 3, there are 3 conditions. Either it has a 0 remainder, so that means it is divisible by 3. If it's not divisible by 3, it has either remainder of 1 or its remainder of 2. And that's it. So the 2 cases is, the first case is that if I mod 3, it has a 1 remainder, or the other case is it has a remainder of 2. But if I change it algebraically, this means that n can be expressed by 3 times some integer plus 1 for some integer, right? So that is, first of all, that is the first step, what I just wrote. This is by definition of n mod 3 equal to 1, we have this thing here. That's the first step. Okay, so since we're running low in time, I'm just going to give you a rough sketch, and I will challenge you to try to do the second part. With the second part, this means n is equal to 3m plus 2 for some m that is integer. Okay, but for the first one, if I have definition, it's 3k plus 1. The second thing is I'm going to do by substitution. So what is the substitution? The substitution rule is that n squared plus 2 is equal to 3k plus 1 squared plus 2, which again, I'm going to use the rule of a plus b squared, which is 9k squared plus 6k plus 1 plus 2, which is equal to 9k squared plus 6k plus 3. And the third step is by factoring 3. So n squared plus 2 is equal to 3 times 3k squared plus 2k plus 1. And then the next step is by closure property of integer. If I define c is equal to 3k squared plus 2k plus 1 is integer. So now n squared plus 2 is equal to 3 times c for some c integer. So by definition, now if an integer is 3 times equal to 3 times of some other integer, means that it's now divisible by 3. So now you have proved the first case. You are going to do the second case similarly by substituting n as 3m plus 2, and you do exactly similar process. Okay. All right. So I'm going to stop streaming, and feel free to ask me additional questions and so on.